This is Team TrumpCard. The project assigned to us is to implement a computation offloading algorithm based on game theory for vehicular edge networks. We know that the number of vehicles are increasing every day, and as we are working towards automated vehicles, the vehicles are expected to perform a lot of computations, but their computation capabilities are limited. Here, our objective is to reduce the latency of the computation offloading of vehicles using mobile edge computing. Here, we prefer mobile edge computing over mobile cloud computing because of its efficiency. In mobile cloud computing, every task is performed by the central server, whereas in mobile edge computing, computations are performed at the edge of the network. Now, the main question is, how is this a game? This is a decision making problem among multiple vehicles. This is nothing but a collision game where the vehicles work towards finding the right server to request for computation such that the overall computation overhead is minimized or optimized. We consider various factors to find the right server. We find the resultant computation overhead for each and every channel and choose the optimal one or do the computation locally. This is how we find the computation overhead. And here, the Nash equilibrium is achieved when no vehicles can further decrease the overhead by changing its decision. So, vehicle N looks at decisions made by other vehicles and formulates its own strategy such that the optimal decision is obtained. Now, let's look at the implementation. On the left, we have the algorithm that we have tried to implement in our project. So, by default, the vehicle strategy is set as 0, which means the computation is done locally by default, and psi n of t will just store the best response at each and every iteration. So, these 10 lines of code are executed parallelly across all the n vehicles and in each and every time slot. So, the time slot at each and every time slot, these particular piece of code is run iteratively until the best or the optimal strategy is obtained. And on our right, we have a project. Here, we are just trying to find the uplink data rate, which in turn is used to find the transmission rate. Here, rmin, this function will return the decap value at each and every iteration, and this tn function is used to find the computation overhead for a given strategy. Now, this is the algorithm that is on our left. We have just tried to implement it in Python. Here we can notice that 77 is the decap value and 97 or 133 is the value of the chosen strategy. So this loop runs until the obtained strategy is equal to the optimal strategy. Here, according to this setup, server 3 choosing server 3 will result in optimal strategy. So at that point of time, the loop just stops and that server is just sent a request, and if the server accepts the request, which is at random, then the computations are sent. Here we're just trying to find the performance of our application or the algorithm. Here on our left, we have the graph that has been obtained in the original research. First, what we're trying to do is we're just trying to find how bandwidth affects the computation overhead. So here, omega is the bandwidth value, and we're just varying it from 1 to 20. By default, the omega value is 6. So here, Tn is we're just finding computation overhead for each and every omega value, and on plotting the graph, we can see that bandwidth, sorry, the computation overhead value just decreases exponentially when the bandwidth increases. And similarly, we just change the input value. Here, an is the array of input size. We're just changing it from 1 to 20. So when we just change it and find computation overhead, we can see that the computation overhead increases linearly when the input size increases, which is also similar to the result that has been obtained in the original research. And this is the complete implementation of a project. Thank you for listening patiently.